Yeah. Good morning to one and all. Good morning. So you please kindly confirm audio video on screen once. Please kindly confirm the audio video on screen. Right. So yesterday we are discussing about the capacitance calculation of the 3-core cable. So now the C per phase, if you check capacitance per phase value, that's coming as CS plus 3cc. CS plus 3cc. Now our attempt is to find the values of CS and CC. Our attempt is to find the values of CS and CC by conducting some experiments. Okay. So the next heading what we are going to take here is methods, or you can say experiments for the calculation of CS, CC, and as well as C per phase. Okay. Yeah. So let's say here experiments to be conducted. Experiments to be done for the calculation of CS, comma, CC, and C per phase. Yeah. Experiments to be done for the calculation of CS, CC, and C per phase. Simple, very simple. So we'll be taking up a 3-core cable first. We'll be taking up a 3-core cable. Right? So we are going to do some set of experiments, what we said, for the calculation of CS, CC, and C per phase. Very simple to understand. Look here. So just you will take one cable to the lab, 3-core cable to the lab. So let us show that 3-core cable here. So this is one 3-core cable I am showing, right? Like this we have. These are the conductors. I will show 1, 2, 3 conductors. Core 1, core 2, core 3. Core 1, core 2, core 3. So this is a core 1 we have. Yeah, next, I'm showing core 2. And then we have core number 3. Like this. 3 conductors we have. Right? Core 1, core 2, core 3. And this was sheath. Sheath which is not grounded now. We are taking the cable to the lab, right? We are taking that cable to the lab, so that sheath is not connected to ground. That's the thing. Okay, next, listen. See, in this experiment, first experiment I am saying you directly, then thereafter I will tell you what we are doing and why we are doing all these things. Okay, in the first experiment, what I will tell you is core number 2 and 3. Core number 2 and 3, I will connect to sheath by using some wires in the lab. I will connect core 2 to sheath as well as core 3 to sheath. After connecting that, I will measure the capacitance from the remaining core. What is that? 1 to sheath, we will measure the capacitance. Okay, yeah, see. So I am connecting this core number 2 to sheath. Similarly, core number 3 to sheath. And we are expecting to get the capacitance calculation or capacitance measurement between number 1 and sheath. This is experiment number 1, what we are going to see. Okay, see, listen. After taking this cable to the lab, for example, if it's a 3-phase cable, operating or rated voltage is 11 kV. We are not applying 11 kV to that. We are not applying 11 kV voltage to that. Just we are taking a piece of cable to the lab without any supply, and there we are connecting the core 2 to sheath and core 3 to sheath, and we are about to measure the capacitance between number 1 and sheath. How to measure capacitance in lab? Maybe by using some shearing bridge. We will measure the capacitance value. We'll get some number. For the capacitance. Okay. After that, this cable diagram with that connection, what you have done practically, we have drawn on paper. Like this. And we will keep the CS and CC wherever it is available. We'll keep the CS and CC. And we simplify this equivalent circuit to find out effective capacitance from core 1 to sheath. That equation what you get now in terms of CS and CC, must be equals to number what we got from lab. Number what we got from lab. All of you getting it? All of you getting? I will explain again and again. Just go through it. First, I will say experiment number 1. I will keep this one in the next slide. I will keep this one in the next slide. Experiment number 1 to be done for the calculation of these capacitances. Experiment number 1. See, in this experiment, any two cores connected to sheath, any two cores connected to sheath, and capacitance measured between remaining third core to sheath. Third core to sheath. That's the thing what we are doing. Any two cores connected to sheath and the capacitance measured between the remaining third core to sheath. Okay. Practically, for example, practically in the lab, let us say, practically in the lab. So I am saying that core number 2 and 3 connected to sheath. Or 2, 3 connected to sheath. Okay. Capacitance measured between core number 1 and sheath. Okay. Capacitance measured between that core number 1 and sheath. Yeah. So let us say this capacitance measured in the lab is something like C1. Okay, measured value. It's a number actually. I am saying it is C1. It's a perfectly known number for me that we calculated from the experimental. All of you understood till this point? Please tell me. I need your response here. All of you understood till this point? Yes, good. Okay, so this is a practical experiment setup what we said. Second step, what I am saying, that cable diagram we have drawn on the paper. After drawing that on the paper, whatever the thing we have done practically, core number 2 and 3 connected to sheath, I have joined it. And we have to measure the capacitance between core number 1 and sheath. Okay, now you keep the CS and CC in this model, available capacitances in this model. Very simple. See, already I said conditions for the formation of capacitance. Two conducting bodies should exist. Between the two, there should be some dielectric medium and there should exist a potential gap. Then only that capacitance will be appreciable for us. Capacitance we have to take into the analysis. Okay, fine. Tell me now, can we get any capacitance between 1 and sheath? I need your answer. Can we get any capacitance between 1 and sheath? Yes. What's the reason? Not connected. That's it. First two conditions will satisfy always. Third condition we should check. If these two are not connected, there may be a potential gap, definitely. So capacitance will exist definitely between 1 and sheath. That number is CS. 2 to sheath, do you have any capacitance? All of you please tell me. 2 and sheath, do you have any capacitance? No, we don't have. Why? What's the reason? Because both are joined together, both are operating at same potential, no potential gap. 3 and sheath, do we have? 3 and sheath. No capacitance between 3 and sheath. Okay, 1 to 2. 1 to 2 do we have or not? 1 to 2, yes we have. 1 to 2 we have, that is CC. And 1 to 3 also we have, that is CC. 2 to 3 do we have? 2 to 3, anybody? 2 to 3, tell me. 2 to 3. No. 2 to 3 you don't have. 2 to 3 we don't have. What's the reason? Both are connected by sheath now. Both these two cores are connected by sheath. Okay. Now we have to find out the expression for this capacitance, and we should make it equals to the number C1 what we have done earlier. We have to find out the expression for the C1 and we should make it equals to C1 number. Okay. See, I will redraw this model. I will redraw this model. All of you listen. All of you listen. Total 4 points I have. Total 4 points. Core 1, core 2, core 3, sheet. 4 points. Core 1, core 2, core 3, sheet. This is core 1 point. What about core 2? Is it same as 1 or different? Different. Core 2 is different from 1. Core 3, it is same as 2. Core 2, core 3 is same as 2. Because 2 and 3 are joined together. Sheet, same as 2 and 3. Same as 2 and 3. So 2, 3 sheet, all the 3 will be same. Now, you keep these 3 capacitances in this model. Keep the 3 capacitances in this model. See this. 1, 2 sheet, 1, 2 sheet CS. 1, 2 sheet, we have CS. 1, 2, 2 CC. 1, 2, 2 CC. 1, 2, 2 CC. Next. 1, 2, 3 again, we have CC. 1, 2, 3 CC. 1, 2, 3 we have CC. Now, we have to find out the effective capacitance from core number 1 to sheet. That we should make it equals to C1. How these 3 capacitance are connected? Parallel. What's the parallel equivalent now? CS plus 2CC. CS plus 2CC is a parallel combination of that is equal to C1. Is equal to C1. Yeah. Tell me now, in this equation, what we have done, which are the known values and which are the unknown values here? In this equation, which are the known and which are the unknown values? Tell me please, known value. Known value is what? Known value. C1 is known. CS and CC are unknown. C1 is known. CS and CC are unknown. But you have 2 unknowns of single equation, right? 2 unknowns of single equation. It is not possible to find the 2 unknowns. It's not possible to find the 2 unknowns. Then what you should do? We will do one more experiment with a different connection. One more experiment with a different connection. Then we will get another equation in this manner. And then we'll solve the 2 equations together to get the 2 unknowns. So this is equation number 1, what we are getting from the result of the experiment 1. Experiment 1 result. Next thing. Experiment 2 I am taking up. Experiment number 2. Experiment number 2. So in this what we'll say is bunch all the 2 cores, sorry, all the 3 cores together. Bunch all the 3 cores together or connect all the 3 cores together. All the 3 cores together and find capacitance from any one core to sheet. Capacitance from any one core to sheet. Capacitance from any one of the core to sheet, we can say. Okay, practically in the lab, after conducting this experiment in the lab, I calculated this capacitance something like C2. Calculated this capacitance practically from the lab, something like C2 number, some number you get. Practically from the lab, we got this number as C2. Got this number as C2. Okay, now let us do that theoretical study on the paper. Just observe here. So I have shown the cable diagram something like this. Okay. Conductors I am showing 1, 2, 3. Force you can say. Force 1, 2, 3 force. So it's a core 1. Core number 2. And similarly, core number 3, we can say like this. Core number 1, 2, 3. And it was a sheath which is not connected to ground, I can say. Sheath which is not connected to ground. What I can say now? Bunch all the 3 cores together. Or you can say connect all the 3 cores together. Yeah, see this. So I am connecting core number 1 to 2, 2 to 3, 3 to 1 like this. Bunch all the 3 cores together. 1, 2, 3 are joined together by using some wires. Okay, next. Between what you have to measure the capacitance now? Between any one of the core two sheath, we have to measure the capacitance. Any one of the core means maybe you select as core number 1, doesn't matter. And sheath. Between these two, we should measure the capacitance. Okay, that number may come as C2. That number we should make it equals to C2. Okay, yeah, next thing, present. So we have drawn the cable diagram on the paper. Now we have to keep that CS and CC in this diagram. Just look here. Between 1 and sheath, do we have any existence of capacitance? Between 1 and sheath, do we have any capacitance existing? Yes, definitely. Because not connected together means we have some capacitance as Cs. Between 2 and sheath, yes, not connected together, capacitance will be existing. P and sheath also we have that capacitance Cs. Okay. Yeah. So let's see here. So again, we have 4 terminals here. 1, 2, 3, and then sheath. 4 terminals we have. 1, 2, 3, and then sheath. You see here. This is core 1 we have. Core 1. What about core 2? Same as core 1. Core 2 is same as core 1. Both are same. What about core 3? Same as 1 and 2. Same as 1 and 2. 1, 2, 3 are same. 1, 2, 3 are same. And this is a sheath we have. This is the sheath. Okay. 1, 2, 3 are same, and that was a sheath. Now we observe. 1, 2 sheath, we have CS capacitance. 1, 2 sheath, we have CS capacitance. 2, 2 sheath also we have CS capacitance. 3, 2 sheath also we have CS capacitance. You don't have any capacitances existing between the conductors. Right? Existing between the conductors, because all the 3 cores are punched together. Now we have to find out the effective capacitance from core number 1 to sheath. Core number 1 to sheath, that I am saying as C2. Then how these three are connected? Parallel. That will be 3 CS equal to C. I can write. I can write here 3 CS is equal to 3 C2. And this you take up as equation number 2 from the experiment 2 result, and you solve equation 1 and 2. Equations 1 and 2, you will get the values of CS and CC. Okay. Let us say from equation number 2, you can write directly. From equation number 2, you can write CSC is nothing but C2 by 3. Na? Capacitance CS is equal to C2 by 3. C2 by 3. Now, you write from equation number 1. Right from equation number 1, CS plus 2CC equal to C1. CS plus 2CC equal to C1. CS value, we can keep it as C2 by 3 plus 2CC. Okay, and this is C. From this, 2CC is equal to C1 minus C2 by 3, and CC equal to C1 by 2 minus C2 by 6. CC equal to C1 by 2 minus C2 by 6 we can get. This is capacitance between any two conductors. Capacitance between any two conductors. Okay. CC equal to C1 by 2 minus C2 by 6. Now, already you know CS and CC. By using these two, we can find out the capacitance per phase, which is CS plus 3CC. Already we have got the formula for capacitance per phase, right? Right. So I can say in the next slide. So therefore, capacitance per phase, already we know it as CS plus 3CC, and the CS is C2 by 3 plus 3 times of CC. CC is C1 by 2 minus C2 by 6. C1 by 2 minus C2 by 6. From this you can get 3C1 by 2, 3C1 by 2, and you simplify this one. It will come to be minus C2 by 6, I think. Minus C2 by 6. Please check that. C1 by 2 minus C2 by 6. Is it so? Please kindly check. Good. This is the capacitance per phase. See, the intention is very simple now. You just do the experiment number 1, means connect any two cores to sheath and find out the capacitance between the remaining third core to sheath. Okay, find out the capacitance. Second experiment. Bunch all the 3 cores together, find the capacitance between any one of the core to sheath. After getting those values, so-called C1 and C2, directly substitute in this equation, you will get the value of capacitance per phase. Capacitance per phase. C per phase you are going to get. C per phase. Yeah, done. So we have one more experiment. Maybe I'll say third experiment now. Experiment number 3. Just look here. Experiment number 3. Experiment number 3. Experiment number 3. Observe here. Experiment number 3. Connect any one core to sheath. Any one core to sheath. Connect any one of the core to sheath. Okay, and measure capacitance between remaining 2 cores available. Remaining 2 cores available. We have to connect the capacitance between the remaining 2 conductors or 2 cores available. Okay, and practically in the lab, let's assume that any one of the core I am saying, core 2, let's say core 2 connected to sheath. Then we have to measure capacitance between 1 and 3. Okay, so core 2 connected to sheath. Core 2 connected to sheath. Okay, Capacitance has to be measured between core number 1 and 3. Core number 1 and 3. Practically, I got that number. I got that number as C3. Measured value was C3. Measured value was C3. Okay. So now you draw the diagram. Draw the diagram on the paper and give the connection according to the thing what I said. According to the thing what I said, just draw the diagram and give the connection. Give the connection. All of you, please listen. All of you, please listen. See, this is our outer sheet what we said, and these are the conductors I am showing now. Conductors A, B, C are 1, 2, 3 better. 1, 2, 3 cores, we can say. This is a core number 1. And then we have core number 2. Then one more. We have core number 3 like this. Core number 1, 2, 3 we have. 1, 2, 3. Just observe now. Just observe. Listen. See, without giving any connection, according to experiment what you are doing, don't keep the values of CS and CC in the model. Don't keep CS and CC without giving the connection. First you give connection. Then you think about the values of CS and CC in the model. Look here this. Connect core number 2 to sheet I am saying. So I have to connect this core number 2 to sheet first. This is a connection. We have to measure capacitance between 1 and 3. Between 1 and 3, you should measure the capacitance. 1 and 3, you should measure capacitance. And that is C3. That is C3. Now, you keep the CS and CC now in the figure. In the figure, whichever the available CS and CC we have, that you keep in the figure. Okay. Of course, you know it is sheet, right? Check. 1, 2 sheet. Existing because not connected. 1 and sheet are not connected, so definitely this capacitance will be existing CS. 2 to sheet you don't have shorted. 3 to sheet will be existing CS. You can say this one. 1 to 2 existing, that is CC. You can say 2 to 3 also existing, that is also CC. 1 to 3 also existing, that is also CC. Only one capacitance is missing. 2 to sheet capacitance, that is missing. Remaining all capacitances existing in the circuit. Remaining all capacitances existing in the circuit. Okay. Next, listen please, listen. This is a physical model. Physical model. Now electrically, so I'm saying now, please listen. Electrically, I will move this core to sheet. I will move this core to sheet, right? So I can say next case like this. It was a cable we have. Now you see, this is a core number 1 we have, core number 1. And then core number 3 I am showing here, core number 3. Core number 2, I will move on to sheet directly. Core number 2, I will be moving on to sheet. So this point itself, core 2 as well as sheet, both are same. Now you keep the CS and CC in the model. This is 1 and this is 3. 1 to sheet we have CS. 3 to sheet again we have CS. 1 to 3 we have CC. 1 to 2 sheet combination we have CC. 3 to 2 sheet combination we have CC. 3 to 2 sheet combination we have CC. And between 1 and 3 we should measure the capacitance as we are saying now. Between 1 and 3 we should measure the capacitance. Between 1 and 3. Okay, next, listen please. So CS and CC, these two will be in parallel, na? CS and CC, these two will be in parallel. It come to the CS plus CC. And these two also in parallel, that will be coming as again CS plus CC. Okay, so that I will show in the next diagram. Next diagram I will be showing. Let me copy the same diagram in this same diagram. So this is that figure we have. Now this CSE and CSE is getting added up. So it will come to be resultant as CS plus CC, CS plus CC. And you know, again, this CC and CS are in parallel, that is added up, and it will come to be CS plus CC again. Like this, we are going to get the equivalent model. Electrical equivalent. Now, total 4 terminals again. Always we have 4 terminals. That is core 1, next core 2, next core 3, and then sheet. 1, 2, 3 cores, and then we have sheet. Okay, I'll show you. This is core 1. Core 1. And core 2, let us show here. Core 2. Or core 3, I will show first. Then I will go for core 2. This is core 3. And we have this is core 2, let us say. Core 2. All the 3 are different, right? 1 is different, 2, 3 is different, 2 is also different. 1, 2, 3, all 3 are different. What about sheath? Same as 2. Sheath will be same as. Now you keep the 3 effective capacitances in this circuit. 3 capacitances in this circuit. 1, 2, 3, CC. 1, 2, 3, we have CC. 1, 2, 2 sheath, CS plus CC. 1 to 2 sheath, we have CS plus CC. 3 to 2 sheath, we have again CS plus CC. 3 to 2 sheath, we have CS plus CC. Now, you have to measure the effective capacitance between core number 1 and 3. Between core number 1 and 3, we should measure the effective capacitance. Okay, next thing. How these two are connected? CS plus CC and CS plus CC. How these two are connected? Anybody please tell me how these two are connected? Just look at this circuit and tell me. These two are connected in series, right? These two capacitances will be connected in series. Yes or no? So assuming that the sheath impedance is negligibly small, this point and this point will be same. This point and this point will be same. So obviously these two will be connected in series, you can say. These two will be connected in series. So if you redraw this equivalent model, this is a core 1, core 3, you can see. 1, 2, 3, we have CC. And this series combination of CS plus CC and CS plus CC again will come like CS plus CC by 2. And you have to find out effective capacitance between 1 and 2. Effective capacitance between 1 and 3. So now you can write from this. C3 is a parallel combination of these two again. So it becomes CC plus CS plus CC by 2. Okay. So you can get from the experiment number 3, C3 will come like CC plus CS plus CC by 2. So it will come to be CS plus 3cc by 2 as a whole. You can get it like CS plus 3cc by 2. CS plus 3cc by 2. Yeah, please tell me now. Please tell me. CS plus 3cc by 2. Yeah, all of you listen. All of you listen. See, the CS plus 3cc itself is capacitance per phase, right? CS plus 3cc itself is a capacitance per phase. So you can write this one. C per phase by 2, from which you can write capacitance per phase equal to 2 times of C3. Capacitance per phase is equal to 2 times of C3. C per phase is equal to 2 times of C3. 2 times of C3. Okay. Yeah. So let's write. See, actually, the aim what we have said at the beginning itself is for the calculation of CS, CC, and C per phase. Experiments to be done for the calculation of CS, CC, and C per phase, right? See, by the end of the second experiment, first experiment, and we have done second experiment, by the end of the second experiment itself, we got both the values of CS and CC. We got both the values of CS and CC, as well as we got C per phase also. Then why you are doing third experiment unnecessarily? Why you are doing this third experiment unnecessarily? Anybody please tell me, what's the purpose of the third experiment? What's the purpose of the third experiment? Here you can get the C per phase directly. Directly we can get the C per phase, right? This third experiment is very simple. Connect any one of the four to sheath, measure capacitance between the remaining two conductors, multiply that capacitance value with 2, you get the C per phase. All of you getting? But to get the values of CS and CC, at least 2 experiments must be conducted. 2 experiments must be conducted. Maybe it's experiment 1 and 2, or 2 and 3, or it may be 3 and 1 combinations. Okay, fine. So this is about the capacitance calculation of the 3-core cable. 3-core cable capacitance calculations by conducting some experiments in the lab. Why it is so means it is not possible to give expressions for CS and CC. Okay, so I'm writing the statement. It is not possible to give expressions for CS and CC in terms of cable dimensions. So these values, these numerical values will be calculated by conducting some experiments. This is the reason why we are doing these experiments. All of you getting? Right? It is not possible to give expressions for the capacitance of CS and CC in terms of the cable dimensions, like radius of the cable, overall radius of the conductor. So based on these numbers, with respect to these numbers, it is not possible to give expression for the capacitance value. That's why we are finding these numbers. By conducting some set of experiments. Okay, so I think all of you getting it. It will not work here. It will not work. Yeah, so let's take some simple problems on this one quickly. First one I'm taking a. Yeah, go through it, please. A 1 kilometer long, 11 kV, 3-core, 3-phase metal sheathing cable, right? A 1 kilometer long, 11 kV, 3-core, 3-phase metal sheath cable gave the following test results. Number 1, experiment number 1. Connect any 2 cores to sheath and measured capacitance between the 3rd core and sheath is 0.6 microfarads. Okay. Second, capacitance between all the 3 conductors bunched together and sheath is 0.96 microfarads. Effective capacitance of each core to neutral is. Means what his interest is to find out. Obviously C per phase, na? His interest is to find the value of C per phase. So he is asking us to calculate the value of C per phase. See, to know that C per phase value, he has given some set of experiments here. Experiment 1, experiment 2. Okay. See, by using these experiments, as we studied just now, we have to calculate the values of CS and CC. That CS and CC we should substitute in the C per phase equation in order to get the capacitance per phase value. So CS plus 3cc is the C per phase. To know the values of CS and CC, we should conduct these experiments. Okay, first experiment. First experiment. I have a cable like this. Cable, and I'm showing conductors. These are the conductors I will show. Conductors 1, 2, 3, I can say. So it's 4, 1, 4, 1, 4, 2, and then we have core number 3 like this. 4, 1, 2, 3. Next, you say this is 1, 2, 3. What is saying here? What is saying here? Connect any two cores to sheet. Any two cores means maybe 2 and 3 you select if you want. 2 and 3 I will be joining to sheet. And you have to measure the capacitance between the remaining third core and sheet. Remaining third core is number 1, na? So between number 1 and sheet, we have to measure this capacitance, and he said that number already 0.6 microfarads. That number he said already 0.6 microfarad. Now you keep that CS and CC in the model. You keep the CS and CC in the model. It's very simple to write. And here we have CS. 2 to sheet we don't have. 3 to sheet also we don't have. 1 to 2 we have CC. 1 to 3 also we have CC. Then how these three are connected? Anybody? How these three are connected? Anybody please tell me. Parallel. These three are connected parallel. So it will come like 2cc plus CS is equal to 0.6 microfarads. 2cc plus CS will be equal to 0.6 microfarad. Don't ask me how. We have done it already in the experiment number 1. Okay, next. Let's take second experiment. Second experiment. So we have a cable obviously, okay? So we have a cable like this. And I'm showing conductors 1, 2, 3. So this is a conductor number 1. And conductor number 2. And then conductor number 3 like this. 1, 2, 3 conductors here. Right. 1, 2, 3. Next. What he said in the experiment number 2. Capacitance between all the 3 conductors, bunch it together and sheet. So you have to bunch all the 3 cores together like this. Between this bunch and sheet, we have that capacitance to be measured. That number is 0.96 microfarads. 0.96 microfarads. Now we keep CS and CC in this model as usual. 1 to sheet we have CS. 2 to sheet we have CS. 3 to sheet also we have CS. And how these three are connected? Parallel. These three are connected in parallel. What's the equivalent of this parallel? So 3 CS na? 3 CS. That number is 0.96. 3 CS is equal to 0.96. Now solve these two equations, get the values of CS and CC. From this, you know, CS is 0.32 microfarad. And you say this is from equation number 1. You can write the next slide. From equation number 1, 2cc plus CS number 0.32 equal to 0.6, you can say. So CC will come like 0.14 microfarads. You do it and you will get that number as 0.14 microfarads. That's the CC. CC will come like 0.14 microfarads. After getting the 2, capacitance per phase will come like CS plus 3cc. CS plus 3cc. This number may come like 0.74 microfarads. Capacitance per phase will be equal to 0.974 microfarads. So correct option will be B. Correct option will be B. Yeah. Done. So I think all of you getting it. Next we'll do one more problem in the view of this 3-core cable. One more problem we'll take up. 1550. So let's see. See this one. So in a three-core cable, capacitance between any two cores is 0.5 microfarads. Capacitance between any one of the core two sheet is 0.3 microfarads. What is the capacitance measured between any two cores connected together and the third core? Any two cores connected together and the third core. Between that, you have to measure the capacitance value and you should give the number. So it's a type of reverse problem, you can say. It's a type of reverse problem. Now, he said the value of CC 0.5 microfarad, CS value 0.3 microfarad. After knowing the values of CS and CC, he is giving some connection. According to that, how much is C per S? Just look here. Just look. So from the data, he has given CC number 0.5 microfarads and CS number 0.3 microfarads. Okay, so first we will take the cable diagram. We'll take that cable diagram like this. Cable diagram. And you see, I'm showing the conductors 1, 2, 3 now. It's a core 1 and it's a core 2. And you see, it's a core number 3. Core number 1, 2, 3 we have. 1, 2, 3 conductors, and this was a sheet. Observe. What is the capacitance measured between any two conductors connected together and the third core? First, what you have to do? You have to connect two conductors together. Between that and third core, we have to find the value of capacitance. Let us say I will join port number 2 and 3 together like this. And I was interested to measure the capacitance between this 1 and 2, 3. Between these two, we have to measure the capacitance value. Okay. Yeah, so I'm sorry. Uh, please kindly check this. CS and CC distribution in this model. CS and CC distribution in this model. Okay. So 1-2 sheath, definitely we have some capacitance like the CS here. CS. 2-2 sheath also we have some capacitance as CS. 3-2 sheath also we have a capacitance of CS. Like this. 1-2 sheath, 2-2 sheath, 3-2 sheath. 1-2-2. We have CC. 2-2-3 we don't have. 2-2-3 we don't have. Okay. 1-2-2. 1-2-2 we have a capacitance of CC now. Now we observe. CS will be in parallel now. So it will come 2 CS. CC will be in parallel now. 2 CC. 2 and 3 are same terminal. 2 and 3 are same terminal. Let me show in the next figure. Next figure. It's a cable we have, and I'm showing first port number 1 here like this. As we said just now, 2 and 3 are same, so I'm showing here this is 2 and this is 3. Port number 2 and 3 are same. Okay, it's 1 and it is 2, 3, and you observe 1-2 sheet we have CS. Yes. And these two are in parallel. It's a 2 CC value. And it's 2 CS value. And we have to get the capacitance between number 1 and 2. Number 1 and 2. Okay, fine. So let me redraw this model again. This is a sheet, of course. Let me redraw this model. This is 1. 2, 3 are same. Just now we said 2 and 3 are same. And this is sheet. Okay, sheet. Now 1, 2, 2, 3 we have 2 CC. 2 CC. 1-2 sheet we have CS. 2-3-2 sheet we have 2 CS. And we have to get the equivalent capacitance between 1 and 2-3. Between 1 and 2-3, we should get the equivalent capacitance required. So CS and 2 CS will be in series. CS and 2 CS will be in series. This is 1. This is 2 and 3. It is 1, 2, 2, 3. We have 2 CC. And series combination of CS and 2 CS. Series combination of CS and 2 CS will be CS into 2 CS by CS plus 2 CS. It will come like 2 by 3 times of CS. And this is the equivalent capacitance which we need. So I can write now C equivalent equals to 2 CC plus 2 by 3 times of CS. 2 CC plus 2 by 3 times of CS. Yeah, very good. Most of you are giving correct answer. CC 0.5 plus 2 by 3 times of CS is 0.3 given. So this number will come 1.2 microfarads. Sometimes we get a question which is out of our experiments also. That's the intention. We may get a question which is out of from the experiments also. Okay, this is not in our set of experiments, right? But still he is asking a different view of capacitance calculation. Yeah, done. So if you have completed, please raise your hands. I will be moving to the next topic in this cables, that is losses in the cables, or you can say causes for heating in the cables. So next slide, I am showing causes for heating in the cables. Heating in the cables or losses in the cables. Causes for heating in the cables, or you can say losses in the cables. Look here. See, what are the various losses we can experience in the cable? What are the various losses we can experience in the cable? First one is I square R loss in the conductor. It's a regular loss what we can get in any cable, right? I square R loss in the conductor. I can say I core square into R core. Loss in the conductor. the core or conductor. I core square into R core loss in core or conductor. It's a general loss which will exist for any conductor. Second one. Dielectric power loss in the cable dielectric material. Dielectric power loss in the cable dielectric material. Cable dielectric material. Third one is sheath loss and armoring loss. Sheath loss and armoring loss. Sheath loss and armoring loss. Okay, done. Sheath loss and armoring loss. I square R loss in the conductor, dielectric loss in the cable dielectric material, sheath loss and armoring loss. Okay. Second one. So first one I know need to discuss. Second one and third one you see. Second one we will put more concentration. Okay. Second one, dielectric power loss in the cable dielectric material. Dielectric power loss in the cable dielectric material. Dielectric loss. Yeah, very simple equation, right? Very important also for ESC prelims as well as for GATE examination, both. Listen all. For example, we have a dielectric material existing here like this. Dielectric material. Dielectric material. And you see, for this dielectric material, we are applying some voltage V at certain frequency. For this dielectric material, we are applying some voltage at certain frequency. How this dielectric material will be represented in the electrical equivalent circuit? How this dielectric material will be represented in the electrical equivalent circuit? Yeah, anybody please tell me how this dielectric material represented in the equivalent circuit? It will be represented as RC circuit. It will be represented as RC circuit. Particularly, I will show some resistance and capacitance in parallel. Right? So we'll be showing that as a RC parallel circuit, in fact. Plus minus voltage V, and this is a resistance, and this was a capacitance. Like this. And this is a current I, you can say. A resistor will draw a current of IR, and capacitance is going to draw a current of IC. Capacitance will be drawing a current of IC. RC parallel circuit. Like that, we are going to model. Like that, we are modeling the dielectric material. So, in such a way, generally, if you look at this single core cable, right? Just observe now. It's a conductor and this is a sheath, which is grounded. Sheath is grounded. And you see here, this is a dielectric material existing between core and sheath. This is a dielectric material existing between core and sheath. That dielectric material, I am going to represent as a RC parallel circuit. That dielectric material we are going to represent the form of RC parallel circuit. This is a way of understanding exactly. That's a way of understanding exactly. Okay, next. Whatever the R we are keeping in the circuit now, that itself is representing the dielectric power loss. R will be representing the dielectric power loss. Dielectric power loss. Okay. Whether this R value is equals to insulation resistance? Anybody please tell me? Whether this R value, is it equals to insulation resistance? Yes or no? No, it's not exactly insulation resistance. No. It's not exactly insulation resistance. Formula what we have written, rho insulation by 2 pi L into Ln of capital R by small r. That's not that. There is some other reason. For this dielectric loss here. Okay, I'll tell you. Very simple. See, if you keep a dielectric material in the presence of an external electric field, for example, this is a dielectric material we have, and we are keeping that in the presence of an external electric field. What will happen to that material? Anybody please tell me? we are keeping the dielectric material in the presence of an external electric field, what will happen to that material? It will be polarized. It will be polarized. Okay. And there are some dipoles formation, and these dipoles will be aligned in certain direction. These dipoles will be aligned in certain direction. Okay. Next. Listen, please. Listen, please. See, whenever this electric field direction is getting reversed, what will happen? Obviously, polarization direction will be reversed, or you can say dipole alignment direction is going to be reversed. During the reversal process of the dipole alignment, definitely these molecules are going to consume some energy. These molecules will consume some amount of energy, which will be dissipated in the form of heat. This is going to be called as dielectric power loss, or you can say hysteresis loss mainly. Mainly it is called as hysteresis loss, or else you can call it as dielectric hysteresis loss. Okay, now I'm writing the statement. Kindly go. If the applied electric field direction is reversed. Then the dipole alignment direction or polarization direction will be reversed. Polarization direction will be reversed. During this reversal process, right, the molecules will consume some energy, which is called as dielectric hysteresis loss. Okay, which is called as dielectric hysteresis loss. Yeah, from this explanation what we have made, who will decide the dielectric loss now? From this explanation what we have made, who will decide the dielectric loss? Tell me please. Number of reversals. If the number of reversals are more, obviously hysteresis loss will be more, na? Number of reversals, who will decide now? Frequency of operation will decide. So I can say dielectric hysteresis loss will be proportional to frequency of operation. Dielectric hysteresis loss proportional to frequency of operation. Number of field reversals or number of flux reversals, that you can say as frequency of operation. Okay, let's move back. See, actually, listen here. Actually, in this what we call dielectric material equivalent circuit representation, I have two resistors. One is a resistor which is representing the hysteresis loss quantity, RH. RH is representing the hysteresis loss component, and there is a general resistance, body resistance, so-called R insulation, right? There is a general resistance, that is R insulation. And parallel combination of these two will be the effective resistance which is causing the power loss in the dielectric material. Following all of you. So R is equal to parallel combination of the hysteresis component resistance and insulation resistance. Hysteresis resistance and insulation resistance. Parallel combination will give the effective resistance to be kept in the circuit. I think all of you getting it. Yeah. Now I can say dielectric class consisting two parts. One is hysteresis loss component. Next component is power loss due to insulation resistance. Power loss due to insulation resistance. I am calling it as V square by R insulation. Calling that as V square by R insulation. Two losses we have. One is hysteresis. Next one is V square by R insulation. V is operating voltage. Na? So V square by R insulation is a power loss due to insulation resistance. But you see, among these two numbers, V square by R insulation number is negligibly small. For example, I'll tell you. Total dielectric loss is something like 1000 watts. 1000 watts. In that, maybe this V square by R insulation is only 50 watts. Remaining 950 will be hysteresis component. Following the reference. So V square by R insulation is negligibly small. So major component of the dielectric loss is hysteresis loss would be. That's the interest to tell you. Okay, fine. Next, this is major component. Let's move ahead. Now, from the circuit, what's the formula for dielectric loss? V square by R, V into IR, V into IR. Next, IR square into R. Dielectric loss formula from the circuit. Come to the V square by R, IR square into R. Else you can write it as V into IR. V square by R, IR square into R here. Next one we are saying is V into IR. Till again, I explained many things about the hysteresis loss. Again, you are asking me, it's an insulating material, how that loss is. Okay, fine. Just check this one. Next. See, I will be taking up one phasor diagram for this. I will be taking up one phasor diagram for this one by taking voltage as a reference. First, I will draw IR current, next IC current, then I will go for net current I. Okay. Then we will think about some more things about that dielectric material. Right. Phasor diagram. So I am taking voltage as a reference. Voltage I am taking as reference like this. Voltage reference I'm showing. First, I should keep IR current. IR current will be in phase to that voltage, but the current magnitude is very, very less. Practically I am saying you that IR current magnitude is very, very less. I am sure. This is IR current. How is IC current? 90-degree leading. That quantity is a big one. IC current is a bit big one. Okay. I will show like this. IC current is a bit bigger. Now we have to add this IR and IC together. IR and IC we have to add together in order to get the resultant current flow in the dielectric material. And that we are going to get, that resultant current we are going to get as this. So this is the current I we can say. That's the current I, resultant current. I. Yeah, write it here. Practically speaking, that IR current is very, very less compared to IC. Practically speaking, that IR current is very, very less compared to IC current. And what's the practical current we have? I is a practical current. IC is an ideal current to be expected. I is a practical current in the dielectric material, and IC is a ideal current to be expected. Whatever the angle gap between these two we have, that I am naming as delta, displacement angle. Delta is called as displacement angle. Okay, delta is called as displacement angle. Displacement angle. Okay, let's move. It's a right angle triangle. Na? It's a right angle triangle. What is tan delta? What is tan delta from this right angle triangle? This is IR, right? So you can get IR by IC is tan delta. Resistor current by the capacitor. IR by IC, that is tan delta. Now, what is IR? You can say IR is equals to IC into tan delta. IC into tan delta. You keep it aside. We will use this in the dielectric power loss calculation. Dielectric power loss calculation. Let's continue with the tan delta a little bit. Let's continue with the tan delta a little bit, which is called as loss tangent. Loss tangent. Tangent. So tan delta is equal to IR. IR by IC. What is IR? You can write from circuit. From circuit, what you can write IR? V by R. V by R is a current IR. What is IC? V by XC. V by XC. So you can get here V by R. And here you can get V by XC. So it will come to be XC by R. Na? Comes to be XC by R. What is that XC? 1 by omega C. XC is 1 by omega C. So it will come to be 1 by omega RC. 1 by omega RC. That is the loss tangent. Loss tangent is 1 by omega RC. You can see 1 by omega RC. Yes. So I think all of you getting it. Okay, next. See, listen. If there is no power loss in the dielectric material, all of you please tell me. If there is no power loss in the dielectric material, then how is the current IR value? How is that current IR value? Zero, na? That current IR will be zero. So if that current IR is equal to zero, then IC and I will be same. IC and I will be same. Delta will be zero, right? Delta will be equal to zero. So there is no displacement angle. There is no displacement angle. Okay, fine. If power loss is increasing in the dielectric material, means if this IR is increasing like this, IR is increasing like this, then resultant current I will fall down, delta will increase. So I can say, with respect to increment in the loss, current IR is increasing, delta is also increasing. Hence, we are going to call this delta as loss angle of dielectric material. Loss angle of dielectric material. Loss angle of dielectric material. Practically speaking, this number is very less, like 2 degree, 3 degree. For a healthy material, for a good material, for a healthy and good dielectric material, this loss angle will be very, very less, like 1 degree or 2 degree in that manner. Okay, yeah. Let's move with the dielectric loss formula. V into IR I am taking. In the place of IR, I will be substituting IC into tan delta. IC into tan delta. Okay, let's continue. V into IR, you can say. So it will be V into IC tan delta. IC into tan delta. So it is V into what is IC? V by XC. IC is V by XC. So you can write now V square into what is 1 by XC? 2 by F into capacitance value into tan delta. V square by XC means V square into 2 by FC into tan delta. So from this you can know dielectric loss is proportional to voltage square, frequency, capacitance into tan delta. Voltage square, frequency, capacitance into tan delta. But the delta is a very low angle. Na? Delta is very, very low angle. So that the tan delta we can write approximately delta. Tan delta we can write approximately delta, but it's in radian, as delta is very low. Delta is very, very low. I can say tan delta will be approximately equals to delta in terms of radians. So that you can call this dielectric loss will be proportional to voltage square, frequency, capacitance into delta radians. Voltage square, frequency, capacitance into delta radius. Done. So is it clear? Clear? Next thing. So for example, if you think about a three-phase cable, for a three-phase cable, if you write, first dielectric loss per phase. Dielectric loss per phase will be simply phase voltage square, same equation, huh? Same equation I will write. V square 2 pi f c tan delta, but here V phase square 2 pi f c per phase tan delta. Okay. V phase square 2 pi f c per phase into tan delta. That multiplied with 3 will give dielectric loss 3 phase. Multiplied with the 3 will give 3-phase dielectric loss. V into phase voltage square 2 pi f c per phase. Okay. So dielectric loss 3-phase will be equals to 3 into phase voltage square into 2 pi f c per phase into tan delta. We can say this is for the 3-phase cable. Yeah. So this is about the dielectric loss we have discussed. Next one we can say sheath loss. Sheath loss. Sheath loss and armoring loss will be more or less same way. Yeah. So next heading can say sheath loss. Sheath loss. See, for example, I am discussing with respect to a single core cable here. It's a single core cable. Single core, single phase cable, AC cable. Single core, single phase, AC cable. AC cable. And you know, this is a conductor we have, core, I can say conductor, carrying some alternating current. The sheath is grounded in here. Sheath is grounded. Core is carrying some alternating current of I core. I core. I will write that formula something like √2 into core current RMS value into sine omega t. Actually, Im sine omega t will write the current in the instantaneous form. It will be Im sine omega t, but I'm writing it as √2 RMS current. √2 into RMS current is peak current. √2 into RMS current is peak current into sine omega t. See, listen. See, whenever this is carrying some alternating current like that, right? It will be producing some magnetic flux. Producing some magnetic flux like this. And that magnetic flux is going to link with the sheath. That magnetic flux will be linking with the sheath. Right, phi. Phi core, it's a AC flux produced by the core. AC flux produced by the core. Next step. That is interacting with the sheath, causing an EMF in the sheath like ESH. ESH is EMF in the sheath. EMF induced in sheath. Induced in the sheath. And because of that EMF, definitely the sheath is going to carry some current which is diverted to ground, of course. It is diverted to ground. That you can say as sheath current. ISH. You can call as sheath current. Sheath current. And sheath loss is nothing but simply that sheath current square into sheath resistance. Sheath loss we are going to name as sheath current square into sheath resistance. Sheath current square multiplied with the sheath resistance. Right? That's the loss. Actually, this induced EMF we have now, sheath induced EMF. The sheath induced EMF will be equals to mutual induced EMF. Sheath induced EMF is a mutual induced EMF. So M into di core by dt. Like this we can write. Mutual induced EMF M into di by dt. So it is M into di core by dt. What is that M? M is a mutual inductance between core and sheath. M is a mutual inductance between the core and sheath. And if you write RMS value of this EMF, you will get like M into omega into core current RMS. M into omega into core current RMS. M into omega into core current RMS. Okay, so I think all of you getting it. Flux will penetrate even through insulator, magnetic flux. Magnetic flux will penetrate through insulator also. It will be having relative permeability as 1, like just like air, just like air. Air is an insulator, right? Yeah. Right. Now, 3 losses we have discussed till now, right? First one, we can say I square R loss in the conductor. Next one is a dielectric loss, and the last one we said sheath loss. Okay. Tell me, what will happen to these 3 losses if length of cable is, if conductor current is increasing, then if frequency of operation is increasing, if length is increasing, these. Okay, let's see. First one. If core current, or you can say conductor current is increasing, core current, or you can say conductor current is increasing, what will happen to I square R loss? That will definitely increase. There is no doubt about it. I square R loss will be definitely increased. What about dielectric loss? What about the dielectric loss if that conductor current is increasing? Almost constant. Almost constant. Simply, you substitute I core equation here. I core is root I core into sine omega t. You substitute here. Do the differentiation. Okay. You get the peak value. Divide it through 2, and you will get this one. Do that. Do that. Substitute I core. See, dielectric loss value mainly depends upon the operating voltage of the system rather than the current. So I can say with respect to current variations in the conductor, the dielectric loss value will be more or less constant. Dielectric loss value is almost constant. It's almost constant. Okay, and what about the sheath loss? Sheath loss will be increased because of the current increment. Because you know that sheath induced EMF value proportional to core current. Sheath induced EMF value proportional to core current. That's why I can say sheath loss is going to be definitely increased if the conductor current is increasing. Conductor current is increasing. Okay, next one. If the frequency of operation increases. If the frequency of operation increases, what will happen? Tell me. I square R loss increases because of increment in the skin effect and the proximity effect. It is a skin effect and proximity effect, right? So I can write now. I core square into R core increases little because of skin and proximity effects. Skin and proximity effects. Because of the skin and proximity effects, there is an increment. There is an increment in the I square R loss. I square R loss. Next one. Dielectric power loss, you know, it is proportional to frequency. Directly from equation itself, you can say that. Dielectric loss is proportional to frequency. So if frequency is increasing, dielectric loss also increases. And sheath loss also increases. Sheath loss also increases. The reason, you know, that sheath induced EMF is proportional to omega. Sheath induced EMF will be proportional to omega, means proportional to frequency. So if frequency is increasing, sheath induced EMF is more, sheath loss is also more. These are the variations in the losses with respect to frequency. Next one. If length of cable is increasing, See, if length of cable is increasing, of course, you know, I square R loss is increasing. I core square into R core, this loss is increasing. And dielectric loss anyhow increases. Right? Because you know that R is the shunt element, right? Dielectric loss, a simple formula if you write, it is V square by R. Na? V square by shunt resistance. R is a shunt resistance is that. So as length is increasing, shunt resistance value will decrease. If shunt resistance value was decreasing, then obviously dielectric loss is going to be increased. Length is increasing, shunt resistance value decreases, so dielectric loss definitely increases. And next one is a sheath loss. It definitely increases because of more mutual linkages. Because of more mutual linkages between conductor and sheath, the sheath loss also increases. See, listen, all of you. See, the observation made here is the overall loss in the cable becomes very, very high as if its length is increasing. So that the heat generation in the cable will be great. Means high amount of heat is going to be generated in the cable, right? Because of this much amount of heat generation, there may be a possibility for the damage of the cable if length of the cable is increasing. There may be a possibility for thermal damage of the cable if length of cable is increasing. Beyond certain length, we can't use a cable in the view of the thermal damage. So I can write now. As length of cable is increasing, overall loss in cable, greatly increases. Overall loss in the cable greatly increases. So the heating in the cable is high. Heating in the cable is high. Our cable is getting overheated. You can write that implies there is a possibility for thermal damage. There is a possibility for thermal damage. There is a possibility for thermal damage. So, in the view of this thermal stability, of cable, we should not use the HVAC cable for whatever the length you want. That length is generally limited to 50 kilometers. Okay, right. So, with respect to thermal stability, always HVAC cable length is limited to 50 kilometers. Has to be used only for the length less than 50 kilometers. It has to be used only for the length less than 50 kilometers. Respect to thermal stability of the HVAC. Next one. Let's think about the HVDC cable here itself. Let's think about the HVDC cable losses directly. Losses in the HVDC cable. Losses in the HVDC cable. I square R loss, do we have it or not? I square R loss, do we have it or not? RSH is a resultant shunt resistance in the circuit, including dielectric loss and all. Yeah. See, definitely we have the I square R loss. There is no doubt about it, I square R loss. But how is that value in DC compared to AC? That is less. Why in the sense? We don't have any skin effect and proximity effects here. Okay. So I can say here, I square R loss is existing, but it is very less. I square R loss in the core, I core square into R core, it is non-zero, but it is low. It's a low value. Okay. Next, what about dielectric loss? Dielectric loss will be approximately equals to 0 because 0 frequency of operation. Major component of loss will be 0 now. This hysteresis loss will be 0. There may be an existence for V square by R insulation. There may be an existence for V square by R insulation, which is negligibly small. Neglected. And sheath loss will be approximately 0. Sheath loss will be approximately 0 because no frequency of operation means no induced EMF in the sheath. No induced EMF means no current flow in the sheath. So obviously sheath loss will be 0. So I can say now the overall loss in the cable is negligibly small in case of DC operation. So I can say overall loss is very low. The DC cable, I'll write overall loss is very low. Loss is very, very low. So that heating will be less in the cables. Heating will be less in the cables. Heating will be less in the cables. Okay. Heating will be less in the cables. So is it required to keep any length limit on the HVDC cable now? Is it required to keep any length limit on HVDC cable? Not required. You can use this HVDC cable for whatever the length you want. Yes or no? Right. So I can write. So there is no length limit on the HVDC cable, practically speaking. There is no length limit. Length limit on HVDC cable. Upper length limit we are saying. Upper length limit always. HVDC cable. Okay, next. Next thing, you please tell me. What about HVAC overhead line? Anybody? HVAC overhead line. Do you have any length limit on HVAC overhead line? HVAC overhead line length is limited by 500 kilometers with respect to steady state stability limit of the system. Less than 500 kilometers with respect to angular stability line. Angular stability of the system. We have to keep that length limit as 500. What about HVDC overhead line? What about the HVDC overhead line? Do you have any length limit on HVDC overhead line? No length limit. So I can write no length limit. No length limit on the HVDC overhead line. So almost 4 categories we have discussed here. 4 categories. HVAC overhead line cable. HVDC overhead line cable. 4 categories. What will be the practical application of these things? What will be the practical application of these things? Listen please, listen please. HVAC overhead line, is it practical or not? Yes, most of the times, whatever the lines we see outside are HVAC overhead lines only, right? HVDC overhead line, yes, it is also practical. To transfer bulk amount of power for longer distances, we are going for HVDC overhead line sometimes. So HVAC overhead line practical, HVDC overhead line is also practical. Both overhead lines are practical. Okay, next. HVAC cable, is it practical? All of you please tell me. All of you please tell me. HVAC cable, is it practical or not? Yes, very practical. Even in big buildings, also, the people are using HVAC cables for interconnection from substation to the building. Right? HVAC cables are very practical in the system. Even in generating station also, we'll use HVAC cables for the interconnections. Right? HVAC cables also practical. What about HVDC cable? What about the HVDC cable? Is it practical or not? HVDC cable. Is it practical or not? Tell me please. See, we have one situation here, practically speaking. For example, practically speaking. See, listen. So we have 2 countries here which are separated by water. So one is our India. Other one is our neighborhood nation, that is SN, Sri Lanka. Listen here, listen. India and Sri Lanka. Between that we have Bay of Bengal, ocean. See, we decided, let's say we decided to transfer power from one country to other country. Means exchange of power from one country to other country by using one power transmission link. Okay. See, this power transmission link, what you are saying now, it should run in the sea. It should run in the ocean. So overhead line you can't use, definitely. If you want to run in ocean, it is not possible to use the overhead line. Then what line we have to use? Cable we have to do. Cable means again 2 types. One is AC cable, other is of DC cable. Particularly, this length is around 70 kilometers. From this point to this point is around 70 kilometers. If that is 70 kilometers, more than 50, so you can't use AC cable. There we should go with the HVDC cable. HVDC cable. And that HVDC cable we should run in the ocean. Should run in the ocean, or we have to keep that down to the sea, down to the sea. This cable we are going to name as submarine cable. Submarine cable. We can call it as HVDC submarine cable. HVDC submarine cable for the power transmission. Power transfer between India and Sri Lanka. We are using practically this the cable. India and Sri Lanka. Actually, HVDC was introduced into power system network in the world, I am saying, in the world view, by means of this HVDC submarine cable to transfer the power between two countries which are separated by oceans, which are separated by water. We have to use a submarine cable, HVDC submarine cable. This is one of the very practical application. Yeah, it's really existing. That's what I am saying. Huh? Undersea cable, like that also you can see. Okay. So these are various applications of cables, and this is the end of this chapter, cables chapter. Have a break for 5 minutes. After that short break, we will be starting that overhead line insulators. Overhead line insulators will be starting. So I have resumed audio video on screen. Audio video on screen. Yeah. So the next chapter, what we have is overhead line insulators. Overhead line insulators. Already you know where we'll be keeping this overhead line insulators means between tower and the power conductor. We are keeping that overhead line insulator between tower and power conductor. Yeah, that's right. Overhead line insulators kept in between tower and power conductor. Tower and power conductor. What are the properties required for these overhead line insulators? And what are the materials we are going to use? These two things we are going to use. Properties. Properties of the overhead line insulators. See, as usual, we discussed about the underground cable dielectric material. So, in similar to that, it requires to have high dielectric strength, obviously. High resistivity, it requires to have high resistivity. These two are necessary properties, right? These two are necessary properties. Any other properties required? Any other main properties required for this overhead line insulators? Any other main properties? Non-hygroscopic, because we keep these overhead line insulators outside the atmosphere. It should not absorb any wet content or water content, you can say. Non-hygroscopic, right? It should not absorb any wet content or water content. Next one, high mechanical strength, or you can say high tensile strength to hold the conductor. High tensile strength, or you can say mechanical strength. High tensile strength, or you can say it is high mechanical strength, etc. These are some of the properties required. Sufficient. Okay, next one. Materials, materials. What are the materials we are using for overhead line insulators? Porcelain is the most famous material what we are using now. Glazed porcelain. Glazed porcelain. Okay, next one. Glass. Glass with high mechanical strength, which we can say toughened glass. Toughened glass. Glass with high mechanical strength. Toughened glass, we can say. Okay, next one. Glazed porcelain, toughened glass, and then we have steatite. Steatite. It's a combination of magnesium and silica. Magnesium and silica combination, right? Steatite. And we have some material like synthetic resin. Synthetic resin. These are various materials. We have. Glazed porcelain, toughened glass means glass with high mechanical strength, steatite. And then one more thing we are saying here is a synthetic resin. These are the materials. So which material we are using famously means mostly we will be using porcelain, and glass also we are using for insulators at 765 kV level nowadays. We have high tensile strength. We are using glass also present days in 765 kV. Steatite is also one material what we are using in the present days. Which is some what we call white color insulator you can see outside. White or ash color insulator you can see outside. That's of steatite. Okay, next one we'll see what are the different types of overhead line insulators. 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 First one, it's a pin type insulator. Pin type insulator. First one is pin type insulator. Second one, shackle type insulator. Shackle type insulator. Third one, string insulators. String insulators. So actually, string insulators is of two types. String insulators is of two types. One suspension, next one is of strain. Glazed means smooth surface. Glazed means smooth surface. Yeah, string insulators, we said two types. One is suspension type, and the next one we are going to call as strain type. Two types we have, suspension type string. Second one we are calling as strain type string. And next, fourth one we can say, stay wire insulator. Or you can say guy wire insulator also. Stay wire insulator. Or you can say guy wire insulator. And next we can say, next one we are going to call as post insulators. Post insulators. These are different types of overhead line and different types of insulators we use. Different types of insulators. Okay, let's see this. See, particularly in substations, particularly in case of substations, you can see some rectangular structured poles, right? You can see some rectangular structured poles in the substations in this manner. Maybe the purpose of this rectangular structured pole, maybe to keep some bus bar on that, or to keep some current transformer, power transformer, potential transformer, something. Maybe I want to keep a bus bar on this. Let us say we are interested to keep one bus bar on this. See, that bus bar we can't keep directly on the pole, right? Pole, we have to provide some insulation support. So we have to provide some insulation support, means like this, we are providing some insulation support we are providing like this. This insulator, what we kept here, is called as bus bar insulator. And this is a best example for post insulator. It's the best example for post insulator. It's an example for post insulator. Example for the post insulator. Bus bar insulator, it's one of the best example for the post insulator we can see. Okay, yeah. So my intention is to tell you these post insulators we will be using in the substations. Used in substations mainly. Used in the substations. So now we will think about these three briefly: pin type, shackle type, and stay wire. And our main concentration will be on the string insulator, string efficiency calculation, how to improve the string efficiency of it. Okay. So first one we are going to take up, that is pin type insulator. First one we are taking up here, that is pin type insulator. Pin type insulator. Actually, we have two types of pin type insulators here. Two types of pin type insulators. One, single shell pin type. Second one, multi-shell pin type. Two types of pin type insulators. Number one, single shell pin type insulator. Second one, we can say as multi-shell pin type insulator. Multi-shell pin type insulator. Two types of pin type insulators here. First one we will say single shell. Second one we are saying as multi-shell. Actually, this single shell pin type insulator is used for low voltage distribution system. Used for LV distribution system. LV distribution means 220 volts single phase level, we said. Next one, 415 volts three phase level. 220 volts single phase level, and then 415 volts three phase level. For that, we will be using the single shell pin type insulator. Next one, multi-shell. It is used for HV distribution. Used for the HV distribution like 11 kV and 33 kV. Like 11 kV and 33 kV. Means my intention is to tell you this pin type insulator is used less than or equals to 33 kV. Used for less than or equals to 33 kV only. So you write here used for voltages less than or equals to 33 kV. So above 33 kV, we should not use a pin type. It may not be economical. One reason. Other reason, the size of the insulator may be bulk. Size of the insulator may be bulk in size. I will show you these single shell and multi-shell pin type insulators to you. Single shell and multi-shell pin type insulators. Just observe. One minute, please. I think I have listed those images of pin type. Okay, anyhow, I will try to show in a diagrammatic way. Just check this one. Check this one. See, this is some cross arm I have. Cross arm. Cross arm. Okay. And here we have some metal pin that will be pushed into cross arm. Pushed into cross arm. On the top of this metal pin, we have that insulator body. Insulator body. Just check here. See, this is some upper shell I am showing, upper layer. And then we have number of bottom shells, top shell, you can say, and we have number of bottom shells, and you can get the insulator structure something like this you can observe. On the upper surface, you will be having some curvy portion, something like groove, called as groove. Upper portion, we have a curvy path called as groove, through which we are going to pass the conductor. This bottom one, I am showing in a blue color. This is called as metal pin. Blue color one is called as metal pin. And this black color as a whole called as insulator, and we have top shell and bottom shells. It's called as top shell. And these two are called as bottom shells. Top shell and bottom shells. Okay. Why we are keeping these many number of shells here? Sorry, there was a network issue. Yeah. Next, let's see this. So we have top shell and bottom shell. Why we are keeping these many number of bottom shells here means, particularly during rainy seasons or winter season, there may be some water drops falling on the surface of the insulator, or there may be some dust depositing on the surface of the insulator. Because of leakage current will increase. Leakage current will increase. So if you are keeping these many number of shells, definitely you can say the dust or raindrops, whatever you say, that will be deposited only on the upper shell, so called the top shell. And bottom shells are almost free from dust and raindrops deposition, so that we can say these bottom shells are going to offer a good resistance for the current, good resistance for the leakage current. Right. So let me write here. Let me write. Bottom shells are protected by top shells. Protected by top shell from dust and raindrops deposition. Dust and raindrops deposition. From dust and raindrops deposition such that leakage current will be less. Leakage current will be less. Not only that. If you see, this is a conductor here, it's a power conductor, and we have the leakage current flowing from this conductor to cross arm. Conductor to cross arm, we have the leakage current flow on the surface of the insulator. On the surface of the insulator. So obviously, if you keep these many number of shells, the path through which that leakage current is passing will be high. Path through which the leakage current is passing is high. Because of that, definitely leakage resistance value will be more and leakage current will be less. Right? So other reason why we are keeping these many number of shells will be length of leakage current path is more. Length of leakage current path is more. Current path is more. Length of leakage current path is more. You can see. Okay. Next. See, actually, this is an insulator which we can see outside, a big pin type insulator. Big pin type insulator. Generally, we will be using it for 33 kV levels. We'll be using it for 33 kV levels. Now, how is it 11 kV pin type and low voltage level pin type? Just like check here. So I'm showing one insulator here. Something like this. Okay. So this is one insulator I am showing. And it's also multi-shell. Definitely it's a multi-shell, but all are of equal size and small shells. And this is used for 11 kV level. 11 kV level. You know already this is a metal pin, and on the top you will be keeping that conductor, power conductor. The top we are keeping the power conductor. This is used for 11 kV. And I will show low voltage level pin type insulator. So you will be having something like this. So you can see insulator in this shape, right? In this shape you can see. So this is a metal pin, you can say. Like that you can observe. Okay. So again on the top you'll be keeping that conductor. Top you'll be keeping that conductor. And this is 415 volts 3-phase. Else you can say it is 220 volt single phase. 3-phase, and this is 220 volt single phase. Yeah. So these are different types of pin type insulators you can observe outside. According to voltage level, we will be using these insulators. Next thing. Shackle type insulator. Next one is shackle type insulator. Shackle type. See, for example, we have a location of curvature. We have a location of curvature. Curvature means this is the conductor running and it's taking some diversion at some spot, at some location. That conductor is taking some diversion. According to the study what we have done till now, at the curvature location, look at the curvature location, I will be keeping some RCC pole, concrete pole, like this. On the top of this pole, I will be keeping some insulator. On the top of this pole, I will be keeping some insulator, so-called pin type insulator, and we will be sending that conductor through the groove. We are sending that conductor through the groove of the pin type insulator. Through the groove of the pin type insulator, we are sending that conductor. So, are you sure that the conductor is standing perfectly in the groove? Are you sure that the conductor is perfectly standing in the groove? Yes or no? No, because whenever it is taking some diversion, it may not stand perfectly in the groove. Definitely the conductor may come out of that groove, and it may be in touch with the cross arm or touch with the tower. That's the problem. So this type of construction we should not use. Particularly at the curvatures. Then what we suggest is at the curvature location, you keep two poles one beside the other. Maybe like this. I'll say. This is pole number one. And one more pole we are going to keep here. It's not a tilted pole actually. It's not a tilted pole. Right? Like this, you can say pole number 2. See, this is the incoming wire we have, and this was the outgoing wire. Incoming and outgoing wires. Okay, listen. See, in order to increase the mechanical stability of the conductors on the poles, to increase the mechanical stability of the conductors on poles, what we are saying is this incoming conductor will connect to pole 1, outgoing conductor will connect to pole 1, so that incoming and outgoing conductors are perfectly stable, mechanically stable. You can't connect this conductor directly to the pole now. Directly to pole we can't connect it. So that I will keep one insulator in the shape of dumbbell. I will make one insulator in the shape of dumbbell. Okay. So after making that insulator in the shape of dumbbell, that dumbbell we will be connecting to pole like this. Dumbbell we will be connecting to pole in that manner, and whatever the incoming conductor we have, that we will twist onto the dumbbell. So that your incoming wire will be mechanically stable. So this red color insulator we are keeping here, red color dumbbell shaped insulator. Similar insulator we keep on the other side also like this. It's also a dumbbell, and top and bottom of this insulator will be again connected to pole, and this conductor will twist onto this in that manner. And tell me please, do you have any electrical contact between incoming and outgoing wires? Do we have any electrical contact between incoming and outgoing wires? Yes or no? No. So to give that electrical contact, I will be connecting on separate wires, something like this. This is going to be called generally as jumper. It's going to be called as generally jumper. Okay? Yeah. Next. Whatever the insulator we are using in the dumbbell shape, that is called as shackle type insulator. This dumbbell shape insulator is going to be called as shackle type insulator. Actually, this shackle type insulator is used only in the low voltage distribution system. Means less than 11 kV. Less than 11 kV we will be using it. So it's used always for voltage less than 11 kV. Means only for the low voltage distribution system. Sorry, there was a network issue. Disturbing continuously. Yeah, so this is about the shackle type insulator, which will be using only for less than 11. See, actually, yeah, listen. See, what's the purpose of the shackle type insulator means? In order to increase the mechanical stability of the power conductors on the poles. So I can say here, aim of the shackle type insulator is to increase mechanical stability of power conductors on poles at what locations? At curvatures, comma, I can say dead ends, right? And river crossings, railway crossings, all these things. Okay, etc. I will write first, etc. Next thing. Sometimes you can read it as to take the strain away from the conductor. We are keeping this. Take strain away from the conductor. To increase the tension on the conductor. We will be using this one. To increase tension on the conductor. We'll be using this one. Okay, next. To increase tension on the conductor. See, for example, if you look at the river crossing or the railway crossings or canal crossing. For example, if the width of the canal is large, for example, I have a canal here. The width of the canal is very large, but one side you have a pole and other side also we have a two poles, one on another. So canal width is very high. Very high, we are saying. Kindly listen. If that's the case, we have to run one power line between these two. If the width is more, obviously span length is more between the poles. If the span length is more, chance of having more sag. There is a chance of having more sag. So in order to reduce that sag, we are going to keep shackle type insulators on both sides, and we will stretch that conductor as much as possible between the shackle type insulators. Stretch that conductor as much as possible. By that way, we can say definitely sag is going to be minimized. Okay, so I can say to reduce the sag at railway crossings or road crossings or river crossings, or you can say canal crossings. We will be using that shackle type. So this is the purpose of using the shackle type insulator. Insulator's purpose. Okay, yeah. So next thing. So let's say in this way. For example, we have one pole. I'll show you the next slide. For example, we have one pole here. Right. Like this, we have one pole. And we have one cross arm, let us say like this. We have one cross arm. On the top of this cross arm, we have a pin type insulator. And then we have some wires. Okay, yeah. Now, due to some reason, maybe the pole was not perfectly installed into the ground, or you can say the land area where you are installing the pole is having low strength, dusty land, you can say sand area. The pole was not perfectly standing. It is shifting its location continuously in some direction, we observe. We observe that this is shifting its position in certain direction. Let us say that it is falling in this direction, falling in the direction. How to avoid the falling of the pole? How to avoid the falling of the pole? So to avoid the falling of the pole, we have to provide some force in opposite direction. We have to provide some force in opposite direction, so that we will be connecting one wire to cross arm and we'll stretch in opposite direction to the falling direction. We'll stretch that wire in opposite direction to the falling direction in this manner. Okay, this wire is to stay the pole at the given location or at the specified location, which is called as the stay wire. It's called as a stay wire. Okay, next. Please tell me where we have to connect the other end of the wire, stay wire. One end is connected to pole, that's okay. Where we have to connect that other end? Where we have to connect that other end of this wire? To the ground. To the ground means what? See, to the ground means we have to keep some rigid body here. Rigid body. Maybe it's a concrete belt we have to keep. Concrete belt. Keep. And to that rigid body, we have to connect that stay wire. Following all of you. So definitely this stay wire is going to carry a leakage current. Stay wire is going to carry some leakage current. Okay, so how to avoid the flow of the leakage current in the stay wire? How to avoid the flow of the leakage current in the stay wire means we will be keeping some insulator on this. Insulator on this one. This we are going to call generally as stay wire insulator. Stay wire also going to be called as sometimes guy wire. Guy wire insulator. Okay, stay wire insulator, or you can say guy wire insulator. It can be called sometimes as egg type insulator also. Egg type insulator. Egg type insulator. It can also be called as egg type insulator. Yeah, support wire also you can say. You see, Vishnu, generally they will keep the insulator on the stay wire. Wire you will see along with the insulator, definitely. Yeah, next. See, just look back and see what are the various insulators we have discussed till now. First one we have seen pin, next shackle, and the last one we are saying is stay wire. What's the purpose of pin type? Purpose of pin type? To reduce the leakage current flow. To reduce the leakage current flow is a purpose. What's the purpose? Purpose of the shackle type? We said many, like this. These are the purposes. What's the purpose of the stay wire insulator? Stay wire insulator purpose is to reduce the leakage current. Stay wire purpose is to stay the pole. Stay wire purpose is to stay the pole. Stay wire insulator purpose is to reduce the leakage current. Following all of you, right? So let's see next. Let's see. Next type of insulator we have given in the list is, next type is string insulators. Next type is string insulators, which is very important for the examination. String insulators. Next one is string insulators. Okay, next, listen. String insulators means actually these string insulators will be used as a replacement for the previous insulators we have discussed, that is a pin type and shackle type. In place of pin and shackle type, at higher voltage levels, we are using string insulators. For example, I am asking one silly question to you. Can we manufacture a 132 kV pin type insulator like this? Can we manufacture a 132 kV pin type insulator like this? See, I am saying you practically 132 kV, practically pin type is used up to 33 kV, that I know. Up to 33 kV we are using pin type, that I know. But what I am asking is, in lab, can we manufacture a 130 kV pin? Yes, but it's bulk, somebody is saying. Yes, we can manufacture, but it is bulk. Bulk in the sense, immediately what you think is transporting this insulator from comparing to installation is very difficult. Yes or no? That's one. Next one, what you can see is, for example, during transportation at some time, some crack happened for the insulator at some place. Some crack happened for some part of insulator. Then what you have to do? We should replace completely the new one, right? Should replace complete insulator with a new one. That's a problem. One more problem. Can we extend this voltage range to a higher level, 220 kV, 400 kV by making some modifications? May not be possible. May not be possible. So these are various issues. If you are going for a single body insulator for higher voltage levels, like 130 kV, 220 kV, 400 kV, and so on. Right? So the suggestion made by the people right now is, if you are going for higher and higher voltage levels, don't make a single body. Don't make a single body of insulator. Manufacture small size of insulators. Manufacture small size of insulators and you connect them in series according to your requirement. That forms a string. That forms a string. Okay. So the basic definition of string is simply a number of small size discs, or you can say units are connected in series, number of small size discs or units are connected in series to form a string, okay. Insulator discs, you write better. Small size insulator discs are connected in series to form a string. Now, what's the purpose of this string here? What's the advantages we are getting now? Advantages. Easy transportation is one advantage. Easy transportation is an advantage, you can say. Next one. Flexibility in the voltage rating modification. If you want to go for higher and higher voltage ratings, you add some more discs. If you want to go for low voltage rating, reduce some discs. Okay, flexibility in voltage rating variation. Flexibility in the voltage rating variation. Next one. Easy transportation is one thing. Next one we are saying is flexibility in the voltage rating variation. Next one, we'll say replacement. Low replacement cost during damages. Low replacement cost during damages. Low replacement cost during damages. So these are various advantages we can get with the string insulators. Various advantages you get with the string insulators. Okay. Now let's say about disc here. Disc, what we are saying? Disc insulator, which we see outside many times. Normal disc insulator, that cross-sectional view I will give you. Normal disc insulator, cross-sectional view. Normal disc insulator, cross-sectional view. See this. So this is upper surface of the disc I am saying. Upper surface of the disc I am saying. And we have some metal pin at the bottom end. On the upper side, we have a metal cap. So I'm showing here, it's a metal pin. Right? Metal pin on the upper side. Here you have some metal cap. Metal cap. Generally, if you see the bottom of the disc, practically, if you see the bottom of the disc, it's a circular one, of course, circular one. In that bottom, you can observe number of concentric circles again. You can observe number of concentric circles. Number of concentric circles you can observe. So those concentric circles, what you can see in the bottom side, can be represented as some wavy shape. Right? Like this you can see. Right? This is a wavy shape, what we can get at the bottom. Wavy shape. Right. Now you please tell me, which is a position of conductor which is the position of conductor, which is the position of tower here. Metal cap, metal pin. We have na metal cap, metal pin. For which point we connect the conductor? For which point we connect the tower? Tell me please. Metal pin, metal pin. Is it a conductor position or tower position? Conductor position. Metal pin is a conductor location, right? Conductor location. So whereas metal cap, it's a tower location. Tower location. Tower location. Okay. Next. Next thing. So we have a term like creepage length. Creepage length. Very simple term only, creepage length. Just observe the word what I am saying. It is a minimum distance measured between any two metal points. Minimum distance measured between any two metal points. Any two metal points through the surface of the insulator. To the surface of insulator. To the surface of insulator. So minimum distance measured between any two metal points to the surface of insulator. Simple, simple. See this. So these are the two metal points here, and we have to measure the distance between these two, so-called the minimum distance, to the surface. Through the surface means we have to measure this length. This is a length which is called as creepage length. Creepage length. Okay, that is nothing but simply length through which the leakage current is passing. The creepage length, what I have shown there, that is nothing but the length through which the leakage current is passing. Length through which the leakage current is passing. Okay. See, whenever this length is increasing, let's say if this length is increasing, leakage resistance will be increasing. Surface leakage resistance value proportional to creepage length. Creepage length. And you know the leakage current value will be proportional to, inversely proportional to leakage resistance value. Inversely proportional to leakage resistance value. And obviously it is inversely proportional to creepage length. Creepage length. So if the creepage length is more, obviously leakage current will be less. For that purpose, we are providing this wavy shape. Because of that wavy shape, what we are keeping at the bottom, right? Creepage length is more. If the creepage length is more, definitely leakage resistance is more, and the leakage current will be less. Leakage current will be less. Leakage current will be less. Yeah. So I think all of you getting it. Yeah. Next. See, by connecting the number of discs in series, we are framing a string. What is each disc voltage rating? 11 kV. Okay. So each disc voltage rating, each disc rating is 11 kV. See, that does not mean that if the voltage across a disc is more than 11 kV, disc is going to be damaged. That does not mean that if the voltage across a disc is more than 11 kV, disc is going to damage. It's a rating of the disc what we are saying. But it might be withstanding a voltage higher than 11 kV also. Maybe it may withstand up to 18 kilovolts sometimes. Okay, so 11 kV is a rating, voltage rating of the disc here. Okay, let's connect the number of discs in series to form a string now. Form a string. So let's say this is the disc we have. This is the disc. It's a metal pin and the metal cap, what we said. So I'm connecting number of discs in series now. Right? Number of discs in series. So like this, you can say. The string, what we have, string, that we are going to hang to the tower first. The string we are going to hang to the tower, or you can say suspended to the tower. Better you can say it is suspended to the tower. And this you can call sometimes as suspension type string. Suspension type string. You can take that heading. Suspension type string. Suspension type. Suspension type string. And you know, at the bottom end of this, we will be having that power conductor like this. We will be having a clamp at the bottom. Clamp. So this is the power conductor we are saying. Power conductor. And whatever the connection between the two insulator discs we have, that we are going to call as metal link or metal link, or you can say link pin. Call that as link pin, metal link, or you can call it as link pin, link pin. So this is about the suspension type. And moreover, the suspension type string we will be using as a replacement for pin type insulator. As a replacement for pin type insulator, we'll be using it. I'll write it. It is used as a replacement for pin type insulator. Pin type insulator. As a replacement for pin type insulator. Okay. Next thing. Pin type insulators are used up to which voltage levels? Up to 33 kV. Up to 33 kV. More than 33, in the sense 66 kV onwards, we will be using the suspension type string. So, is used for voltage levels greater than or equal to 66 kilovolts. Used for voltage levels greater than or equals to 66 kV. Okay, next one. Strain type string will say just it's a other arrangement. Just let me copy this only. Right? See this. Strain type string. Strain type string, you can say. Yeah. So this is the cross arm here. Cross arm. Tower, which is grounded, you can say. Grounded. So this is the arrangement of the string. This is the arrangement of the string, you can say. So on the other side, you have the power conductor. Here's a power conductor. Done. Next. This is a replacement for what? Shackleton. It's a replacement for Shackleton. Replacement for Shackle-type insulator. Shackle-type insulator. And for what voltage levels we'll be using it? See, Shackle-type is used for low voltage system only, like 415 volts and 220 volts. And this we can use for starting from 11 kV. Even for 11 kV also, you'll be using the strain type string. Okay. So used for voltage levels greater than or equal to 11 kV. Greater than or equal to 11 kV. 11. Starting from 11 kV onwards, we will be using the strain type string. Strain type string. Okay. Yeah. Next. How current is that will be on surface. It will be on surface. Okay. How many number of discs we have to keep for a given voltage level? How many number of discs we have to keep for a given voltage level? That's one thing what we have to discuss briefly. Generally, each disc is rated for 11 kV. What we said? Each disc is rated for 11 kV. And what is the conductor operating voltage generally? Phase voltage. Na? Conductor operating voltage will be phase voltage. How much is a phase voltage? How much is the phase voltage of the system? That you divide with each disc rating, so-called 11 kV. That will give you approximately, not exact, approximately how many number of discs we have to use in a particular string. Okay, so let's say here. Let's say number of discs to be used in the string. Number of discs in a string string will be equal to since per phase voltage of the system, per phase voltage rating of the system by what you can say each disk voltage rating, each disk voltage rating. It will be generally 11. So it is V phase by 11, I am saying. You keep that phase voltage also in kilovolts. Keep that phase voltage also in terms of kilovolts. So V phase by 11, that will give you a number of disks to be used. But it may not give, I said to you, it may not give the exact number of disks all the time. But I will give you one table here, table, certain voltage level, how many number of disks to be used in each and every string. Yeah, follow this ones. Line to line voltage rating of the system. RMS voltage rating of the system and number of disks in each string. Number of disks in each string. Number of disks in each string. Observe here. Line to line voltage rating 11 kV. How many disks we can use means only one. 33 kV level, how many disks we'll use? 3. 33 kV, 3. 66 kV, it will be 5. It will be 5. 132 kV, around 9. Sometimes 10 also will use. Sometimes 10 also. 220 kV, it will be in the range of 13 to 15. Sometimes 14, sometimes 15, like that we use. 400 kV, around 20. Around 20. Even some cases I observed we are using 19 units only. 19. Some cases 21. Some cases 22 also. 400 kV. 765 kV, around 30. 30 to 35. 30 to 35 disks we will be using in case of 765 kV. Now tell me. If I show some system outside, maybe a distribution system or transmission system for you, can you tell me at what voltage level it is operating? At what voltage level it is operating? Are you capable to tell now? See, very simple. See, just by looking at the system, you have to observe what the type of insulator you are using there. If it is shackle, if it's shackle type insulator, it's a low voltage distribution system, you can say. If it's a pin type, you should check which pin. Is it a multi-shell, single shell? Again, in multi-shell, is it a small, big? If it's a big multi-shell, then it's a 33 kV level. Okay. And if the string you are using, just to check how many number of disks you are using in each string. For example, I have seen one insulator outside. Number of disks are 21. Number of disks are 21. What is the voltage level of that? What's the voltage level of that? Tell me, please. 400 kV. Close to that. Close number you should check. Okay. For example, I have seen outside, I have one system where I am using 6 disks. 6 units. What is the voltage level? Close to 66 kV. Close to 66. 5 I have written. Okay. But closest number we have to check all the time. These are not exact numbers again. These are close numbers to be kept in each and every. Like that, just by looking at the transmission system or distribution system, we are capable to tell at what voltage level that particular system is designed. Okay? Yeah. So the next topic what we are going to discuss is line to line voltage is a general voltage rating. That's why I've given. Line to line, it's a general voltage rating. That's why I've given here. But strictly speaking, number of disks will be decided by some places strings are connected in parallel. For example, 400 kV string, I said earlier, 400 kV string, maybe 20 disks on one side, one string, and 20 disks on the other string also. I discussed already, right? In bundle conductors, Harshit. Bundle conductor. In bundle conductor, we discussed. Number of strings connected in parallel. Y means to what we call bear the weight of the conductor. To carry the weight of the conductor, one string may not be sufficient. We have to go for number of strings, maybe 2, 4, sometimes 6 also. Okay? Yeah. Fine. So next topic what we are going to discuss is potential distribution across the string. How that voltage is getting distributed across each and every disk that we have to discuss. Okay, yeah. So tomorrow we will start with that and we'll finish and we'll be going for distribution system. Tomorrow will be the last class. Tomorrow will be the last class. If anybody have doubts, you can raise your hands. I am making all the hands low. I will come back within 2 minutes. Come back within 2 minutes. Come back within 2 minutes. Please raise your hands. Madhuchandra. Madhuchandra.
Sir.
Tell me, Madhuchandra.
Sir, in while calculating the capacitance of 3-core 3-phase cable, underground cable.
Okay.
In second experiment, you used all the 3 cores are connected together, right?
All the 3 cores are connected together. Okay. What's
Okay.
the doubt now?
So in balanced condition, the sum of the current means it's equated to 0, right?
It is not a 3-phase operation there, right?
Sir, but the 3-phase conductor, right?
A 3-phase conductor only, but you are not applying 3-phase supply, right?
Then all their angle at 0 degree, same phase.
Hey, listen, Madhuchandra. I have taken this is a 3-core cable, let us say, this one.
Okay, sir.
I have taken a piece of cable. Is there any supply for that?
No, sir.
Understanding what I'm saying you?
Okay. Okay, sir.
That's what I said at the starting also. If I say I have a 11 kV cable, that does not mean that it's operating at 11 kV now while we are doing the experiment.
Okay.
We
So
have
then
taken
it is
only conductor, not supply.
okay.
You have not cleared. Ask me
Okay,
your
okay.
doubt exactly, please.
Yeah, right. Clarify, sir.
Please tell me again.
Sir, in 3-phase 3 cores are connected together means in
3
balanced
cores are
condition.
connected together, but
Means,
there is no supply for the 3 cores already.
okay.
Just you connected the 3 conductors together first. Then between that and sheath, you are applying the voltage for capacitance measurement.
Okay.
Understanding?
Okay, okay. Yeah.
Sorry, in the shearing bridge, you will be keeping that unknown capacitance, right?
Yes, sir.
The 2 terminals will come out from shearing bridge, across which you should keep the unknown capacitance.
Okay.
1 terminal we keep to sheath.
Okay.
Other
Sir.
one we keep to bunch of 3 cores.
Okay. Okay.
Okay, that will give the capacitance value.
Okay.
But it's not a 3-phase cable operation there. It's not 3-phase operation. That's why I have not written ABC. I have written only 1, 2, 3.
Okay. Sir.
I don't know whether you
Thank
have
you,
cleared or not.
Yes, sir. Clear, sir.
Yeah.
Yes, sir.
Okay.
Thank you, sir.
Any more doubt here?
No, sir.
Sir, good morning, sir.
Tell me. Good morning, Vishnu.
Sir, in these things, as of now, we have like all these things we have studied. What are the most things we have to emphasize for gate, sir? Gate alone.
Gate alone means you pick up second chapter LNC calculations and then steady state analysis.
Okay, sir.
Complete, and then go for voltage control.
Those 3 units which has problems.
Yeah. And in cables, insulators, we get some simple questions only.
Yes, sir.
But anyhow, these two will not take much time to revise also. Cables and insulators.
And sir, one more thing regarding this, what we learned, the stray wire, stay wire.
Stay wire.
So the stay wire is the same thing that we find outside our houses for this local transmission.
Yes.
So that's what I asked in that. This also, sir. But
some places they may keep the insulator. Some places that insulator might have damage.
Because whenever I seen, only what I seen is a long iron wire with some grounding. They have used some nail-like structure. That's it. And sir, if you were to touch that, then you will experience a shock or something, sir.
A little shock you may experience, particularly in rainy seasons and winter seasons.
That leakage current will also find a path through our body and go into.
Yes.
And sir, and the major purpose of the stay wire is to, in case during these heavy, like what is a nature catastrophe, if this thing starts swinging, to prevent that swing, we are using the stay wire.
Yeah.
And this shackle type insulator, sir.
Shackle type is to avoid to increase the tension on the conductor, or you can say to make the conductors more mechanically stable on the poles.
Okay, sir. So for that is for like for locally for a particular region, that thing is used, sir. Like for one section of wire.
Yes.
And sir, regarding this multi-shell insulators, you wouldn't like that single shell was not explained. What you explained was multi-shell, no, sir.
No, multi-shell and single shell both are there. Single shell means only one body, right? That's it.
So it looks same like that string insulator, like you explained normal disk.
No,
type.
no, no. I have shown that figure also approximately like this. This one is single cell.
Oh, okay, sir.
Multi-shell.
Okay.
Okay.
Yes, sir. And sir, major one thing. Sir, in this capacitance, while you are explaining this losses, sir,
Hmm.
you did mention that this hysteresis loss is proportional to the frequency.
Yes, yes.
Yet we model that frequency, yet we model the losses resistor. I mean, usually we model like that only, but my doubt is, can't we model it as an inductor, sir? Because it is dependent on frequency, so losses change on frequency means you can say it as
How it's the inductor? You are only saying it's a loss, so we have to represent as a resistor.
Oh, sorry, sir. Real power loss. Okay, sir. Okay, sir. That's it, sir. Thank you, sir.
Okay. Salman Khan.
Good morning, sir.
Good morning. Tell me, Salman Khan.
Sir, can same cable be used for HVAC and HVDC? It only depends on supply.
Yes, you can use it.
Same cable, no, sir?
Same cable you can use it.
Okay, sir. Thanks.
Imtiaz.
Good morning, sir.
Good morning, Imtiaz. Tell me.
Sir, in normal decks, you showed that diagram as a concentric circles in that there, no, sir.
Yeah.
Sir, if you use only one, that it means for 11 kV, sir.
11 kV.
11 kV length, sir.
11
If you
kV
use
only
that-
one disk you are saying.
Yes, sir. Only one concentric circle is shown.
No,
as
no,
a
number
diagram.
of concentric circles will have generally at the bottom of the disk, if you see, you can find number of circles.
No, sir. I seen outside, sir, some places they are
Hmm.
using only one that concentric circle.
One
That's why,
circle,
sir.
Imtiaz. You see bottom of the disk, bottom.
Yes, sir.
You
Sir,
see
could you open that paper?
Are you using only one disk?
Only one disk in have many concentric circles, sir.
That's it. That's what I am also saying. Only one disk with number of circles.
It means for 11 kV.
11 kV. Normal disk only one disk you are using for 11 kV. I am saying.
Okay, sir. Sir, in multi-shell, you said no, sir. There, yeah, I saw in somewhere places they have more than 5 shells, sir. It's been for
That is
the
a
30.
steatite insulator, white color, ash color. No.
Yes, sir.
That's a
It's
different
been for
insulator.
it's meant for the 33 kV, sir. If you have 5 shells in that.
No, that we can't say exactly. That depends upon its size also. Size is also going to be changed.
Okay, sir.
Hmm.
Sir, in HV lines, we are using straight up insulator. Have the many silver type, no, sir. Is it same as our porcelain in?
No, wherever you find that is silver color, where you are using.
In some low distribution set, where I saw, sir, 5.
Is
in
it
have
big or
5
small
shells, sir.
size? Big or small?
Small, sir.
That is a steatite. That insulator is steatite insulator, not porcelain.
Okay, sir.
Okay.
Sir, you saw means you shown in the last some slides in the figure of the abundant conductor. Some insulators are there, no, sir. It's looking like a stake means like a silver color, only, no, sir.
Where you have seen that you have seen silver color?
Yes, sir.
That's also steatite only. I'm saying wherever you see silver color, it's a steatite. Polymer material it is.
Okay, sir. Can we difference when we use the porcelain and the straight types?
That depends upon their requirement only. In present days, the people are going for steatite insulator. Steatite material I'm saying you. Material is different, not porcelain. It's a different material they are using for insulator.
Okay, sir.
Okay.
Sir, in aesthetic class, you said that, sir, R is equal to less than 0.368.
Yeah.
Smaller. Sir, in that, if you want to design same as that conductor, you are using the safety factor in that, sir, or else we can we can add.
Yes. Always after finding electric field intensity on the paper, that you should multiply with the safety factor to go for the dielectric material selection.
Okay, sir. Sir, one more, sir. In that,
Hmm.
I saw in some data sheet they are using derating factor in that, sir.
Derating factor that will come, that may not come for these things, no?
I saw in some data sheets.
For what? For what you have seen derating factor?
Cable, sir.
That maybe that what you call this material strength liability and all.
Okay, sir.
Dielectric material strength liability.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.